Changing data, it seems so simple, right? You click save, you update a record, and just like that, the world is different. But underneath that simple click lies a surprisingly complex and even dangerous reality. So what really happens inside the machine when we ask it to change just one tiny piece of information? Well, the answer reveals a hidden world of risk and some truly brilliant engineering.
Okay, so let's take a really simple task. Our whole goal is to move 100 units from account A to account B. At the human level, that's one single logical idea. But down at the machine level, that one idea shatters into at least two separate operations, and that's exactly where the danger creeps in.
What if the system crashes right in the middle of that? After the money has left account A, but before it ever arrives in account B. And that question, right there, is why writing data is just in a different universe of complexity compared to reading it. It's the ghost in the machine that we have to protect ourselves from.
To really get why the solution is so clever, we first have to feel the problem in our bones. So let's imagine a world without any of a database's protections. A world where we're just updating a plain old file on a disk.
So our little application, it's pretty naive, right? It just follows the most obvious steps. First, it reads the balances from the file. Then, it subtracts 100 from account A's value in its memory. And finally, it starts to write that new lower balance back to the file. And then, right in that exact moment, bam, the power goes out. The whole system just dies. We never even got to start the part where we add 100 to account B.
So what are we left with? A completely inconsistent world. The money is just gone. It's vanished from the system. It left account A, but it never showed up in account B. This isn't just some little bug. It's a catastrophic failure of the system to keep track of its own truth. And this is the exact nightmare scenario that databases were built to prevent. So how do we guard against this kind of chaos? Well, databases give us one single, incredibly powerful idea: the transaction. This is the fundamental promise the system makes to us, and it's our shield against this kind of partial failure. And that promise, it's called atomicity. It's a simple but profound idea. It means those two separate things we wanted to do, subtracting from A and adding to B, they get bundled together into this single all-or-nothing package. They can't be split apart. The system guarantees they either both succeed or the world is left exactly as it was, completely untouched. So when we wrap our operations in a transaction, what we're really doing is telling the database, hey, these changes aren't separate. They are one logical thing. They succeed together or they fail together, period. So how does a database actually pull this off? What's the actual machinery inside that makes this all-or-nothing guarantee work, especially when things go catastrophically wrong? Okay, let's follow the data. Okay, so the first thing you need to know is that this whole process doesn't start on the permanent disk. No, it starts in memory. The database finds the chunk of data on disk that holds our accounts. We call this chunk a page, and it yanks a copy of it into the super fast but totally temporary world of RAM. All right, now that the data is in RAM, the change happens right there. The balance in account A gets updated in that copy. And at this exact moment, something important happens. The page in memory is now different from what's on the disk. It has become dirty. A temporary, uncommitted, and pretty vulnerable version of the truth now exists. But here's the thing. Before the database even thinks about making that dirty page permanent, it does something way, way more important. It writes a note to itself. It keeps this special journal called the log, a running diary of every single change it intends to make. It's the system's memory of what's supposed to happen. And the order here is absolutely everything. The system lives by one unbreakable rule: write-ahead logging. What that means is the log record, that little note to itself about the change, has to be saved to a permanent, safe place before the actual data page gets written back. You secure the intention first, and only then do you worry about the result. This is the whole key to safety. And that brings us to this critical moment, the point of no return, the commit. This isn't just another step, it's a boundary in time. It's a line drawn in the sand. So what is a commit? It's the moment the database formally accepts this new version of the world as the official truth. It's recorded that fact in its permanent log. And from this point on, the system is making you a solemn promise. This change is now real. It will survive. Even if the power goes out 1 millisecond from now, the database is on the hook to make sure this transaction sticks.
All right, so we've seen the machinery, now let's really put it to the test. We're going back to our money transfer, but this time we're going to pull the plug right in the middle of it and watch this whole system of guarantees spring into action.
So picture this. Our transaction kicks off. The page with account A gets pulled into memory, its balance gets changed. We now have a dirty page. But before the transaction can write its commit record to the log, crash. The system is dead. We're left with this half-finished change just floating in volatile memory, but there's no official, permanent promise that it was real.
So what happens? Well, because that change never got to the commit finish line, the system considers it invalid. It was never officially truth. And so the system performs a rollback. This doesn't mean it's literally turning back time. It means it's actively going in and wiping out the effects of that unfinished change, making sure the world is back to the last known good state. That partial truth is just erased.
Okay, but what about the other scenario? What if the crash happens after the commit, after that promise was made? This is where the log becomes more than just a diary. It becomes the blueprint for rebuilding reality.
So the system reboots. The first thing that happens is a special process, the recovery engine, kicks into gear. Its one and only job is to read the log, that permanent memory of truth, and force the main data on disk to match the promises that were made in that log. And this recovery engine basically has two main moves: redo and undo. For any transaction it finds in the log that has a commit record, it performs a redo. It replays those changes to make absolutely sure they end up in the final data, even if they didn't make it before the crash. And for any transaction that it sees started but finds no commit record for, it performs an undo. It goes back and methodically erases any of those partial changes, making sure that unfinished business is never, ever treated as reality. So when you boil it all down, what's the big difference here? A plain file save is basically just crossing your fingers. You overwrite some data and you just hope nothing goes wrong. But a database transaction, that's a guarantee. It creates a clear line between maybe and yes. It promises consistency and it has a rock-solid plan for recovery when things inevitably fail. And that's really what a database write is when you get down to it. It's not just editing a file. It is a controlled, disciplined journey from one consistent state of the world to another. And it's protected the whole way by this incredible machinery of logs, commit rules, and recovery logic, all working together to protect information from the chaos of the real world. So we've just seen this amazing system that protects a single change from the chaos of a power failure. But what happens when the chaos isn't a crash, but comes from inside the system itself? What happens when you have thousands of these protected transactions all running at the exact same time, all trying to change the same little piece of reality at once? Well, that opens up a whole new can of worms, the problem of concurrency.